Correlated Kelvin-probe force microscopy, micro-FTIR, and micro-Raman analysis of doping anisotropy in multisectorial boron-doped HPHT diamonds. Introduction. Diamond is a promising material for high power and high frequency electronics. Today, bipolar and field effect transistors and Schottky diodes have been demonstrated based on CVD diamond. One of the problems that hinders the progress of diamond electronics is the lack of large area substrates for diamond homeopatics. In particular, for the development of electronic devices with vertical charge transport, e.g. Schottky diodes, electrically conductive diamond substrates with low defect density are needed. HPHT diamonds usually reveal inhomogeneous zonal sectoral distribution of impurities, which is due to the selective absorption of impurities by the crystal phase during the growth. As a result, octohedral 111 sectors usually have the maximum content of nitrogen and boron impurities. In order to control the spatial distribution of defect impurity state of diamond crystals, development of local characterization techniques is needed. Measuring the local surface potential by Kelvin force probe microscopy is a fast and informative way of such nanoscale characterization methods. The synthetic diamonds studied in this work were ground by HPHT method. The nanoscope 3A probe microscope was used to study the morphological electrophysical properties of synthetic diamond surfaces. Visualization of residual deformation fields was performed using optical polarization microscopy. Micro-IR mapping was performed using a Nicolet Fourier spectrometer and a Nicolet continuum IR microscope connected to it. In this work, KPFM method is used to quantitatively characterize the variation of surface potential in boron-doped HPHT diamond plates cut parallel and perpendicular to the growth axis. The obtained map of the spatial distribution of uncompensated boron impurity shows a significant sectoral heterogeneity of the impurity composition of the multisectoral diamond plate. The highest concentration of boron is 3 to 10 in 17 order centimeters in -3 order was registered for the growth sector 111, and the lowest is 0.5 to 10 in 17 order centimeters in -3 order for the sector 001. The obtained distribution of the surface potential on the growth sectors shows the highest values for the sector -1, -11, the lowest for 001, and intersectoral jumps of the surface potential. The absorption spectra record typical infrared absorption bands of boron impurities, a single phonon absorption band in the region of 1290 inverted centimeters, and a series of impurity absorption band due to the transition of holes associated with boron acceptors in diamond Lyman series at 2450 and 2800 inverted centimeters. In the low frequency region, a series of bands with a position of 580, 920, and 1040 inverted centimeters are registered, the nature of which is due to the impurity of boron in the diamond. The Raman map shows the fairly stable distribution of the intensity of the main Raman boron band at 580 inverted centimeters within one sector, but a sensitive difference in the transition to another, which reflects the heterogeneity of the distribution of boron impurities in the sectors of the diamond plate. The image shows the influence of the built-in strain fields on the intrasectoral distribution of impurities. Surface potential maps at intersectoral boundaries A and B. A high level of structural perfection of intersectoral boundaries is demonstrated. Absence of twins, massive dislocation walls, impurity gathering, and accordingly the absence of electrically active defects in the boundaries. The features of the band structure of local sections of multisector diamond plates are estimated. Thus, the proposed comprehensive approach allows for reliable estimation of local structural and electrophysical parameters of HPHT diamond plates, which is useful for solving actual problems of diamond electronics.